students, today is our lecture that is related to the method of false position or Regula Falsi method. So this is the fourth method we are studying to solve to find out the root of the non-linear equation. Unlike bisection method, root bracketing is basically Regula Falsi is a root bracketing method, just like the bisection method. And unlike the bisection method, root bracketing is not guaranteed for either Newton's method or secant method. As you know that Newton's and secant, although these both are the powerful or effective methods and fast converging methods, but these two are not a root bracketing method. So if you want to use the root bracketing method, basically that method that splits the interval into sub-intervals, that is called root bracketing method. So if you don't want to use the bisection method, because as you know that the root is guaranteed in the bisection method, but it is relatively a slow method and it requires a very large number of iterations. So if you want to use the root bracketing method and you want to achieve the root within certain less number of iterations, then this method or method of false position or Regula Falsi method is the best appropriate method to choose. So method of false position generates approximation. It is very familiar to the secant method because of its derivation of the formula. It is very closely related to the secant method, and the difference between the secant method and the Regula Falsi method is, first one is that it is root bracketing and secant is not a root bracketing method. Secant method does not split the interval into sub-intervals, and second one is the speciality different from the secant method is that in every iteration of the Regula Falsi method, you require a test of the function's opposite signs. You have to check that, you have to ensure that the functions are of opposite signs, and then you apply the formula, this formula of Regula Falsi method, to proceed between the successive iterations. Although it illustrates how bracketing can be incorporated. So it ensures that how the root bracketing makes it possible to use the less number of iterations as compared to the bisection method. Okay, so basic theme of or construction of the method is you have to choose the initial approximations P0 and P1. These both are two initial approximations, and you have to check that the function values at these 2 points must be or of opposite signs. So the condition is that f of P0 and f of P1, the product of f of P0 and f of P1 must be less than 0. That makes it opposite sign condition. If both are positive, that means both are same signs, then its product must be greater than 0. So that means that root does not lie in this interval, and if both of the function values f of P0 and f of P1 product is negative into negative, that makes it positive, so that is greater than 0. That also means that a root does not lie in this interval. It is only, this condition is only possible f of P0 into f of P1 is less than 0 if one is positive and the other one is negative. So that generates the condition of the opposite signs. And the approximation P2. So approximation P2 is determined with the help of P0 and P1 and f of P0 and f of P1 respectively. So P2 is chosen in the same manner in the secant method, and you use the successive iterations, and if your root within the given tolerance starts to get repeated, then you can stop that iteration or you achieve the root now. So this is all about the construction of the method, and first of all I will derive the formula for the method of postposition. Now, secant method and method of postposition has a very slight difference, and you can see this in the diagram, and that is P0, P1, P0, P2, P3, and okay, so P0 and P1 are basically the interval, and you use P2 and P3 between these. These are basically the approximations, successive approximations between P0 and P1. It is interval. So secant method is, if you use this diagram, you can see that secant method has the P4 outside the curve, but in the method of postposition, the P4 is within the interval. So that means that secant is like a chord, but the point P4 can be outside the curve, but method of postposition, P4 must be within that curve. So this is the basic difference between the secant method and the method of postposition. Okay, that doesn't matter. We come to derivation of the formula. This method is also called method of postposition, or Regula Falsi method is also called root bracketing method, and the second name for this is linear interpolation. We will study the interpolation and linear interpolation in the coming lectures, but it is also known as linear interpolation because here we use the linear slopes kind of concept. Okay, so consider this diagram, and you can see there are basically 3 points on the x-axis. The interval is A and B, and C is any intermediate point, or you can see any intermediate point or midpoint. Midpoint, if it is a midpoint, it becomes bisection. You can apply the bisection method, but C is any intermediate point here by using this IVT, intermediate value theorem. Okay, so the image of A is f of A, and the image of B is f of B as shown in this diagram, in this graph. And you can see f of A and f of B are of opposite signs. F of A is in the 4th quadrant and f of B is in the 1st quadrant. That makes it f of A is negative and f of B is positive. So it means that this Regula Falsi method can be applied here. It is valid here. Okay, so we start to derive this. Okay, so C is any intermediate point here. So if we join the point between f of A and f of B, so the image of C is f of C. So now your coordinate pair becomes of the 3 points becomes A, comma f of A, first ordered pair, and second point is C, f of C, that is the ordered pair, and third point is B, f of B. Now first is we calculated. Okay, by this diagram I can see that you use the concept of the complete slope of A and B, and then using the point C and B and then eliminating it. So in the first derivation I split this straight line about AC and CB. That derives the method of postposition, but here it is the slope of A and B, and that is slope of AB is f of B minus f of A divided by B minus A, and if I use this its line segment CB, then using the point C0 and B f of B, that this makes it the slope m equals to 0 minus f of B minus divided by C minus B. So eliminating equation 1 and 2 m from the equation 1 and 2, that makes it f of B minus f of A divided by f of B minus A equals to 0 minus f of B divided by C minus B. So solving for C, that is exactly derived. You can see that solving for C, we get C equals to B minus f of B into B minus a divided by f of b minus f of b. So that derives it from the secant method. If we use this, we are deriving from the secant method. And if I told you before the split of AC and CB, that also derives the Regula Falsi method. So these two different methods or derivations generates a standard formula, and that is C equals to, C is the next approximation and B and A are the previous two approximations. So C is the successive approximation extracted out of A and B. You can also replace A with x0, B with x1 and C with x2. So x2 is extracted from x0 and x1. So the general formula at each and every iteration becomes A into f of a minus b into f of a divided by f of a minus f of a. Or you can say that it is also equal to, if you take the negative signs common from the numerator and denominator, then it becomes b into f of a minus a into f of b divided by f of a minus f of b. That is also the formula of method of false position. So this is all about Regula Falsi formula. And first of all, what you have to do, you have to take out the in any random interval a and b and select the interval, and this selection of the interval is based on the opposite sign condition, functions opposite signs, and C is extracted from the method. C is basically the Regula Falsi formula, and now C is not the midpoint here because we are not using bisection method here. So C is extracted from the formula A into f of b minus b into f of a divided by f of b minus f of a, and again C is the next point now. So C replaces either A or B depending upon the function's opposite signs condition at each and every iteration. So if C makes it the opposite sign formula, then it becomes the sub-interval here. So now C replaces either A or B, and then you check the opposite sign condition, and then you apply the formula, Regula Falsi formula, again and again to solve, to find out the next root. And if within the tolerance C makes it, the root starts to get repeated with the tolerance, or if f of C starts to appear exactly equal to 0 given the tolerance, then you stop that, and that is the root of the Regula Falsi or any nonlinear equation using the Regula Falsi method. Okay, so now we consider the example 1, and that is consider finding the root of f of x equals to x squared minus 3. So that is the quadratic equation, and you started here because it is a table, but you can also use it manually. You can find out manually, and then you can construct the table out of it. So first of all, we use the random interval, and that is 0 and 1. So at interval 0, the interval is given 1 and 2 here. So if I apply 0, then f of 0 is minus 3, and if I apply the interval f of 1, then 1 minus 3 is minus 2. So both 0, 1 intervals have the same sign, so root does not lie in this interval. So your interval is given here 1, 2. So f of 1 is minus 2, and f of 2 is 1. So that makes it opposite sign. So that means you can apply Regula Falsi method here. So C is extracted from the formula A into f of b minus b into f of a divided by f of b minus f of a. So A is 1 into f of b means it is the value of f of b is 1 minus b is 2 multiplied by f of a is minus 2 divided by f of b minus f of a. So 1 minus minus 2. So by this formula, if we calculate within the 4 decimal places, tolerance C is 1.6663 3 times 6, 7. Okay. So C is this 1.6667 and f of C. Now check that whether C will replace A or B depending upon the sign of f of C. So f of C here is minus 0.221. Obviously C is negative, f of C is negative, so C will definitely replace A here, because it has to compare the opposite signs with the f of b. Now C replaces A, so update C equals to A. So instead of C, instead of 1, I write 1.6667 and B is the same 2. So f of A is minus 0.2221 and f of B remains same, that is 1. So now your formula C is equal to, basically these are the next iterations. So f of A into f of B. So 1.6667 into f of B is 1 minus B is 2 and f of A is minus 0.221 divided by f of B minus f of A is 1 minus 0.221. That makes it C 1.7273. Okay, so C here is 1.7273. Okay, now f of C is, if I apply this in the function x square minus 3, that makes it minus 0.0164. Again, f of C is a negative number, so you have to compare with f of B and f of A. So C again will replace A because of the opposite signs condition of the functions. So so here C will again replace A, and now your A will become 1.7273 and B remains the same 2. F of A is minus 0.0164 and F of B is 1, so C is calculated by the formula of the Regula Falsi method, that is 1.7317, and F of C is 0.0012. Now your C is a positive, f of C is a positive number, so you have to replace this C with the B. Okay, so if you replace the C with the B, then you can sort out, and now in the coming iterations you can see that your root starts to get repeated. And stop this. Okay, the last column is the step size. Step size means the difference between the two successive iterations of C, because C is the updated value. So in third iteration you can still see 0.0044. So if it becomes 0.0000, then you can stop your iteration. So I think that you can continue this by your own self, and you can tell me that by solving by your own self, you can tell me that the root starts to repeat. So do it by your own self. Now this okay, we come to the example number 2, and that is a little bit complicated example that contains e to the power minus x and sine x and cos x. So this is all a combination of these three functions, and interval is 3 and 4. So tolerance is almost up to 3 decimal places. So you use this and construct the table, and you can see that in the after the sixth iteration, note that your step size becomes less than the epsilon tolerance. So that means your root will start appear from the 7th iteration. So do it by your own self, and these are the 2 questions for practice questions and the answer is given, so you can do it by your own self and you can ask the questions from me. Okay, now we do the comparison with the Newton and the secant method. So the example is the previous example we have done before, and that is x equals to cos of x. So the equation is x minus cos of x. So by using the Newton's method, if you use the tolerance up to 4 decimal places, then the Newton method is the last column, third column. So that makes this root starts to appear from the third iteration. Okay, and the secant method, your root starts to appearing again from the third iteration. Okay, third or fourth iteration. But false position, your root starts to appear from third iteration. But in comparison, because it contains almost 9 decimal places, so that shows the difference, that although false position contains somewhat 2 to 3 more iterations than the Newton or secant method, but it is still the fast conversion method as compared to the bisection method. So note that the false position and secant approximations agree through P3, and the method of false position requires an additional iteration to obtain the same accuracy. So it is closely related to the secant method. It contains almost several iterations. Maybe it may be 1 or 2 iterations more than the secant method. So if you have any questions, you can ask me, and it is a very easy method, and this is the last method for to solve the root of the nonlinear equations. Okay, thank you so much